Hello, it's dumplet here. Here's an item on number theory. M and n are natural numbers such that 5 raised to m minus m raised to n is equal to mn. Find all possible ordered pairs of m and n. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. Now, a typical equation in integers, but if you do a lot of questions like these, there's going to be a very obvious observation at the start, and it's that the m raised to n and the mn, they both have a factor of m. And, well, because we have n to be greater than or equal to 1, definitely both of these will be divisible by m. And what that is going to tell us that, well, this 5 raised to m, this should also be divisible by m. So essentially, because of the multiple of m condition, or essentially you could think of it as the mod m condition. So we're going to have m to divide 5 raised to m. All right, so m would have to be a power of 5. Essentially, that's going to be it. But I'm going to split this into two cases, m to be 1 and m to be a power of 5. That is a multiple of 5. So 5 raised to k, but I'm going to set k to be greater than or equal to 1. Now, just to kind of show you that the 5 raised to k is going to work for all the powers of 5, obviously I could put this in, 5 raised to k being 5 raised to k dividing 5 raised to 5 raised to k. And I'll just use the argument that, well, the 5 raised to k, it's going to be greater than k for all values of k, greater than or equal to 1, or for all positive integers k. You can prove this by induction, or you can prove this by just simply taking a look at the graph of those two. Left-hand side is an exponential equation. It is an exponential function. The right-hand side is just going to be a linear function. So definitely the left side grows faster than the right side. So that's going to be pretty much it. But I'll just leave this as an exercise to you guys. And let's try to move on with the question. So essentially, I have two conditions, m equals 1 and the 5 raised to k for positive integer k case. So let me just focus on the easier one, the m equals 1. So obviously the m equals 1 is just going to allow me to substitute m in. So 5 raised to m becomes 5, m raised to n becomes 1. So 5 minus 1, that's going to give us mn, which becomes n. So I'll get an n equals 4. So that's going to tell me from these two, I will have a solution, 1, 4. And you guys could check it on your own, plug it back in here. And yeah, that's going to be one of the solutions. So again, the easier case is done. We just have to focus on the more difficult case. The m is equal to 5 raised to k case. Again, the way we said it, k is going to be a positive integer. So greater than or equal to 1. Now substitute the m in. Now the 5 raised to k technically is raised to the nth power. Laws of exponents, we could multiply the exponents together. So 5 raised to kn. And then for the last term, just simply substitute it in. And, well, again, since n is greater than or equal to 1, this term is going to be divisible by 5 raised to k. And, well, since this already has a factor of 5 raised to k, that's also good. And because of the argument a while ago that the 5 raised to k, it's going to be greater than k for all positive integers k. So surely this 5 raised to k is also going to be divisible by 5 raised to k, which means I could divide both sides by 5 raised to k. And it's going to be this one. So 5 raised to k minus k. Again, laws of exponents, just the quotient rule. Minus 5 raised to kn minus k. And then that's going to equal to n. And because of the divisibility by 5 raised to k, I'm guaranteed to have the exponents here, the 5 raised to k minus k and the kn minus k, to both be integers. Right? So let's try to dig deeper into this equation that we have. And here I try to consider n equals 1. Now, why is that the case? Now, the first one, this exponent, the 5 raised to k minus k, that's definitely positive, following from the argument that 5 raised to k is going to be greater than k. And just subtracting k on both sides, essentially I'll have this thing. So that's definitely positive, so it's going to be divisible by 5. So the first number, it's definitely divisible by 5. But the second number is, well, not always divisible by 5. It's, if n equals 1, this exponent becomes 0. But if n is greater than or equal to 2, so if n is greater than or equal to 2, then this exponent would be greater than or equal to k, and because of the way we set k is going to be a positive integer. The kn minus k would be positive only for the case where n is greater than or equal to 2. Okay, we're just going to go back to it in a while. Let's focus on the n equals 1 case for now. Again, n equals 1 case, we could just directly substitute. So 5 raised to this exponent minus 5 raised to, as I've mentioned, this part becomes 0. So 5 raised to 0 is just 1. So minus 1, that's going to be equal to n, which is 1. Essentially, I'll just have to solve for k in this equation, but pretty obvious that there are no solutions here. 2 is not a power of 5, a contradiction. N equals 1 is impossible. That's done. And we just have to focus on the n greater than or equal to 2 case. And I did mention that n greater than or equal to 2, that's going to make this exponent to be positive. And because this is now a multiple of 5, because it's 5 raised to a positive integer, and this is already a multiple of 5 based from the reasoning a while ago, n would have to be divisible by 5. In fact, n would have to be divisible by the kn minus k. Now, why is that so? Now, n is a positive integer, so definitely the first term is going to be greater than the second term. And both have the base of 5, so I could just kind of compare the exponent. So definitely the first exponent is going to be bigger than the second exponent. So essentially I could just factor out 5 raised to kn minus k. So I'll have 5 raised to kn minus k. So that's factored out. And then the remaining thing would just be 5 raised to k minus kn minus 1, essentially. And this would be equal to n. All right. Now, n, it's going to be equal to a certain power of 5, right? It's going to be a certain power of 5. We don't know what it is, but it is a certain power of 5 times something. We don't know what this thing is, but it's going to be something. So now, since n is greater than or equal to 2, we could kind of write n as the following. So it's going to be 5 raised to this kn minus k. I'm just going to write the second thing as a constant. Now, how do I make sure that this thing is not gonna be too small? Because of the reasoning a while ago that this exponent would be greater than this exponent, definitely this thing will still be positive. So it's going to be 5 raised to kn minus k minus a certain something. I'm just going to call this something c for now. So I'll have n to be equal to, I'm just going to copy this, 5 raised to kn minus k times a certain constant of c. Here is where the problem comes. Because k is a positive integer, so this exponent of kn minus k, it's going to be greater than or equal to n minus 1. So if k equals 1, then it's going to be n minus 1. But n would actually be greater than 5 raised to n minus 1. This is actually true for all values of, it's the other way around. N would be less than 5 raised to n minus 1 for all values of n greater than or equal to 2. Again, you can prove this by induction, or because the reasoning that, well, the right side here is exponential now, and the left-hand side is linear. Now, why is this going to matter? Because, well, we said that n must be equal to this thing. Oh, by the way, this constant, this number should also be greater than or equal to 1 because the exponent here is positive. This exponent is positive. So this number would be at least 5. So like the c we said a while ago, well, it's going to be actually greater than or equal to 4. But, you know, just because for the sake of the inequality here, we can just say it's going to be greater than or equal to 1. But n would be less than 5 raised to n minus 1. So it's impossible for, well, in this case, we're saying we're gonna have n to be greater than or equal to 5 raised to n minus 1, if I really take the bare minimum. So since this thing is true, and we want this thing to be true, definitely it's not possible. It can't be less than or greater than or equal to than the same number. We're going to have a contradiction, and we're going to say that n greater than or equal to 2 this is actually an impossible case, right? So n greater than or equal to 2 is impossible, n is equal to 1 is impossible, so there are no possible values of m. For the case where, going back, for the case where m is equal to 5 raised to k, going back again, we exhausted all our cases, and we only found one solution, the 1, 4. So m equals 1, n equals 4. That's going to be the only solution to the given Diophantine equation. And this will be our sole and final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!